Hello everyone. In this video we will see how we can solve beam by stiffness method. Here in this example we have a beam. This beam we have two members. This is member 1 and this is member 2. Okay, because we have, why we separate, because we have this here support at node B, and also we have a different types of loading that apply on this beam. So the first of all, we should write the global system. That's mean, and we have in the beam we have two. The first one is moment or rotation, and also we have vertical displacement. So how we can know, or how we can draw the rotation and vertical displacement? As you see here in this example, we have point B and point C. They have rotation and also they have vertical displacement. That's mean unknown values. So that, and when we start to make global system, start the first one with rotation and then you can do for vertical. So here we have global system for rotation number 1. I will start from C. Is up to you, but to make it your solution is easy, because if, for example, I make it a rotation here at A, not number A, I will have a problem when I do the big matrix, when I collect the or summation matrix 1 and matrix number 2. So that for easy for you to make it this rotation number 1 and this one rotation number 2 at node B. Rotation number 3, it will be at point number A. Then for vertical displacement, it's also up to you. Here I will start vertical displacement from left to right. So here this is 3, 4, 5 and 6. Okay, so here I'm doing the global system for rotation and vertical displacement. Then after that I should do each, to make it easy for solution, change the supports. I have two supports, roller at B and C, to fixed. Like here, for example, if I make it, this one is fixed, and also for at C also we have fixed. It's just for easy to solution. Let me to install like this one. The member number 1 should be like this, distribution load plus second member like this. Okay, so depends on this drawing we will solve this example. And also to easy for calculate the reaction of moment and also for displacement or reaction. Like here at point A we have a reaction R VA because it's vertical. Here also at B we have R vertical B, and here R vertical C. Okay, and also here we have moment, and here we have moment, and here we have moment. The moment, I mean if we after we put or actually after we change this roller to fixed, that's I mean when I put a moment. Okay, so now, so let me to see. So I didn't explain more. So after you've put fixed, find reaction and moment at point A, B, and C. How can I do that? For at fixed, for reaction, reaction A equal WL over 2. That's mean the load time L, the length of beam number 1, or sorry, member number 1, over 2. You can check the rule of reaction and moment on Google. Equal W is 1 time 9 over 2 equal 4.5 kilonewton. This is the reaction. So now for moment, the moment at point A equal W L square over 12. L is equal 1 time 9 square over 12. The moment, sorry, I don't have any space, over 12, moment equal 6.75 kilonewton time meter. Then same way at another direction or another side. Now I go to B. Also this is assumed is fixed. Reaction at B, same rule, WL over 2. Same values, it will be equal 4.5 kilonewton. And the moment here, also WL square over 12 equal 6.75 kilonewton, because this member is same applied load, is distribution load. Now I will change to another member, is member number 2. That's mean B to C. Here fix it, and also here fix it. Okay, the reaction at B, because we have here different load, so that will be different rule or value. That's mean here, because we have only applied load at the middle of member, so it will be the reaction equal, or the force equal B, sorry, that's me, B over 2. So here we have 10 over 2 equal 5 kilonewton. And for rotation, or sorry, for the, for rotation or moment, equal PL over 8, 10 time L3 over 8, the length, sorry, the rule, this constant, the number 8, it will be equal 3.75 kilonewton time meter. Same rule you can do for at point C. Same rule, P over L, P time L over P over 2. The reaction here, P over 2 equal 5 kilonewton, and the rotation here at point C equal PL over 8 and equal 3.75 kilonewton time meter. So this is the reaction and rotation at each member of this beam. So here now, for non-force, we have the rotation, or before that, sorry, as I explained before, here we have at point B, we have two relation, or two forces, relation. When I take the member number 1, let me to here, this is member number 1 and this is member number 2. Okay, when I take the I find the relation here, I have same relation, this point is B. I mean reaction vertical B and reaction vertical B. It's same point here, sharing point, so that it's summation. So the value here, it will be, when you draw the system, it will be R vertical B plus R vertical B, because same direction. Okay, they pushed the support to the up, so it will be summation here. And for the moment, actually, we have different. This, the direction of moment, and this one also. So I'm sorry. Let me to make it clear. So here in this member number 1, the rotation is clockwise, like this, and in at point P in the second member, it will be anti-clockwise. Okay, like this. So it will be minus here, the sign. That means the moment at point B in the member number 1 minus the moment value of at point P in the member number 2. So that here actually the values of rotation, of moments here, it will be same 6.75 here minus 6.75. That means this value minus 3.75. okay, you will be the total moment at point P after you make it minus. Okay, and this rotation will be same because we don't have, it's not continue, or we don't have any member number 3, for example. Okay, then find the force, non-force. Non-force, if this is from, we get it from moments, okay, number 1, and also number 3, we get it from moments, as you see here, the moment at number 1 and moment number 2. And for non-displacement, we have 4, 5, and 6. This is 4, 5, and 6. Okay. Then go to make your matrix. This is for K1. You will follow this matrix. Okay, and you can make it easy to take out the EI. Yeah, because it's common factor. EI, make it outside and just put it inside here, for example 12 over L3. I mean the constant numbers, okay, and L length, you can put it inside, it's up to you. So here for in the, as you remember, our beam like this, here we have rotation number 1, rotation number 2, rotation number 3, 4, 5, and 6. So as we learned in the previous videos, you take member one by one. So in this one we have member number 1, and this is the direction, is which near point and which is the far point. Okay, this is member number 2. So here in the one we have start with vertical and then rotation. We have 4, we have 4, 3, okay, these values are the number of global system, and the end of beam we have 5 is reaction or displacement, and also we have 2. Okay, just substitute your values here depend on this matrix, and same way we can find the member number 2. One, 2, 5, and 6. Okay, and the total length is 3 meters. Just substitute your values and you will get this matrix, and this is the direction like this. After that, collect your matrix. Okay. This is the fourth matrix, and this is the K matrix, and this is D matrix. The matrix, it's actually easy. Just need spend your time to collect for K1 and K2. Because we have two known forces, so divided matrix for how can I say, it's like just because we have two known values of force, you should find the two rotations, it's unknown values. So you should, by this way, find theta 1 and theta 2, and just take this matrix K11, and this one is called K12, K21, and K22. Okay. Then find the value of theta 1 and theta 2. You can do by any software that you know it, or you can by a traditional way to make it some equations and find the value the values which are unknown. Like here we have theta 1 and theta 2. Then after that, find the reaction, or internal forces. Okay, internal forces, how we can find the internal forces? Just, it's easy just to take the values from matrix. Let me to show you the easy way. Maybe you will not understand from this slide. Internal forces, member number 1, the general law is F equal K dash D plus F FEN. Okay, finite element method. Okay, the F equal, small f equal M1 2. That's mean M from moment 1 until moment 2. Yes, and moment 1 until 2 equal, here I will use KD, it's mean K11, okay, K11 multiply by D. D, here we have theta number 3, rotation number 3, and rotation number 2, plus the values that I got it by WL square over over 12, and the W multiply L square. W multiply by L over 2. You can use this one, the first step actually. So here we have for this one the F capital W L square over 12 and W L square over 12, because here we talk about moment. This is the matrix. So then I should substitute the values. Yeah, I can write here. We have space. So this is the general f equal k d1 k dash d plus f. You can use f node, no problem. Okay, it's just a sign. Okay. F, as I said, it's M12 and M12 moment equal. Here we have talk about member number 1. Okay, member number 1. We will take K11, so I take it EI as a constant, and the value of K11 0.44, 0.22, 0.22 and 0.44. This is K. D theta 3 time theta 2. Sorry, the second member is theta 2 plus, so this one here, 6.75, and we have minus 675. Okay, here theta number 3 we have is 0, and theta number 2 the value is 0.78. Why 0? The theta number 3y is 0 because it's fixed, cannot move. If I go back to the general drawing or the shape, here we have fixed. So theta, this is the theta 1, as I give it a number or a global system. Okay, and this is theta 2 because it's roller, so it's easy to move. This member C or point C move, and also point B can move. But for theta number 3 actually is fixed, so it will be 0, cannot move. Okay, so that I substitute the value of theta number 3 is 0. Okay, then just find the value. You can try and check. For this one, the moment 1 2 equal 6.92 kilonewton time meter, and M12 equal minus 6.40 kilonewton kilonewton time meter. Okay, this is the member number 1 for internal force. Okay, let me to solve how we can do for member number 2. Same way, actually. Member number 2, okay, M23, I mean 0.2 to 3, and also moments at 3 to 2. This is the small f equal, take out EI, and the K matrix here is 1.33 and 0.67, 0.67 and 1.33. Okay, this is the value of K, and for theta we have theta, let me write here. For theta, I mean the D, we have theta 2 and theta 1, because now we are in member number 2. Theta 2 is, we already found it, 0.78. Theta number 1, 2.42, plus F naught, that we find it before the second step after global system. Here 3.75, and the second one minus 3.75. Okay, then just make your calculation, and finally you will get the M2 to 3 equal 6.40 kilonewton per meter. Moment 3 to 2 equal 0 kilonewton time n. So this is our matrix. Then how we can find the support reaction? Actually, this is the last step to draw a bending diagram, moment, and also shear force diagram. The bending moment, let me to show you, depends on the last values that we got it. The bending moment, it will be like this. Let me to change the color. It's look like this. This value here is 6.92 kilonewton time meter. Here the maximum is 3.48 kilonewton time m. Here is 6.40 kilonewton time m, and this one is 4.3 kilonewton time m, and this is already 0. So this is a bending moment diagram for this example. Okay, let's go to shear, how we can calculate it and draw shear force diagram. You can try by your own and check the values or result. So our beam is like this. Okay, the moment here is 692. Moment here 6.40. Moment 6.40. Okay, and here 10. This is distribution load 1 kilonewton. Okay, and this is 10 kilonewton. Then we have here reaction, and also at P you have reaction, and also at A. This is A, B, and C. So support reaction, let summation at moment 2 equals 0. Okay. Reaction C, or let me CY, I call it, time 3. so that the moment here at point the let me to show you. That means I will take it moment about point B, so that summation moment around B equals 0. So Cy, this is Cy, times 3 minus 10 times 1.5, because this is it's already given actually. This is 1.5 displacement, plus 6.40 equals 0. So Cy equal 2.87 kilonewton. Same way, we can find the support reaction at, let's call AY. Okay, so same way, summation at point B equals 0. AY times 9 minus 6.92 minus 1 times 9 times 4.5. This is from distribution load, okay, plus 6.40 equals 0. Then AY equal 4.56 kilonewton. Okay, then finally we have how we can find the reaction at point B. It is easy, just by summation force by y direction equals 0. Then 9 plus 10 minus 4.56 minus 287 minus dy, okay, equal 0. Then by equal 11.57. Then go to shear force diagram. After you find all reaction at all points, so this is our member. So AY is 4.56 kilonewton. Then exactly in the middle, sorry, it's actually I'm very sorry, I don't have any space. Let me to draw again. This is 4.56, okay. Then here equal 4.56. Sorry, I'm very sorry. We don't have anything, it's already 0 here. 4.44 kilonewton. Then go up 7.13 kilonewton. And then how we can get these values? Because we should summation with the values of the load, and because we have shear now, the the reaction or the forces that you find it by WL over 2, like this. Summation with it and then draw. Here is 2.87 kilonewton. So this is the shear force diagram. Okay, thank you for kindly watching and listening. Thank you.